this is out, or some of you cut it out. Okay, so basically then, first, the source, crude oil, secondly, separated on the basis of the different boiling points. And we'll look at that a bit in detail in the next question. I think they ask, how does that work? And we'll go into the intermolecular forces of that, right? So when alkanes are heated at high temperatures in the absence of air, they can break into smaller molecules. So identify the type of reaction. Well, wow, I think this is one of the first things that you can remember probably about this, and this is cracking. Right, so we crack large hydrocarbons into smaller, more useful ones. Okay, write an equation that describes the reaction occurs when heptane is heated in the absence of air to form hexane, butane, and ethene. All right, so we've got that in there. You need to be able to balance. In here, right, at least they do the following. They give the products in there. They say, listen, there's a hexane that forms, there's a butane that forms, there's an ethene that forms. So you can write those down, and then the balance shouldn't be too bad, right? Add up the number of carbons. This is my best tip that I can give you. Look at the number of carbons. When we get to some of the oxidation reactions, I'll show you a quick trick in there. Okay?
Sir,
yes.
Should we show the state symbols in this type of question?
Do you know what? No. For the combustion, it is not that essential. It's not a bad habit, to show the combustion in all the symbols in there. In this case, they are mostly going to be gases, and that's in there, that's produced. So it's fine, show that. I tell you where it is important when we're going to start with energetics next semester. It's essential to have it in there, as well as with equilibria that we're going to deal with. So, it's difficult to tell you, no, not here, yes, there. So it's better to rather show it, because even if you put it in here, the examiner is going to ignore it. So, put gases in there, because this is in any case under high temperature that this is caused, so it's going to be all gases. Does that answer your question?
Now, sir, how do you know what state they are in?
Well, remember, you're doing this under thermal cracking, right? This is thermal cracking, so this is all going to be gases. So it's very high temperature. So that's the easiest answer that I can give you with the cracking. Right, happy with that?
Thank you.
Okay, let's move on to C. And now we've got this complete combustion of ethene. I say calculate the volume in cubic decimeters of carbon dioxide formed in the complete combustion of 1 gram of ethene at room temperature and pressure. Okay, so immediately there's some interesting detail that they give us. They tell us this. They say, listen, at room temperature and pressure, remember, what do we know? We know 1 mole of any substance occupies 24 cubic decimeters. They tell us that we have 1 gram of our ethene, and they ask, listen, what is the volume of carbon dioxide being produced in there? I'm going to do the following, and I left this partially done so that we can work through it together. Just a quick reminder of it. And you know what, when I said in the beginning of the year, listen, organic chemistry is 50% of your question paper. Yes, it's 50% of your question paper, plus they bring in organic equations and reactions with your first part. So it actually adds up to more than that. But let's get back to this. what's the first thing that we can do? If we're going to work with the equation, I want a molar ratio. And this molar ratio is 1 to 2. 1 ethene to 2 carbon dioxide. If I have the mass like I do here, have here, 1 gram, excuse me, I can convert 1 gram to mole. So 1 gram of ethene is 0.036 mole. I can write that in, so it's 0.036. Now I work in my molar ratio. It's a 1 to 2. I don't have 1, I have 0.036. So how many moles of carbon dioxide in there? So times 2, I end up with 0.072 mole of carbon dioxide being produced. But that's not what they asked. They didn't ask what amount of mole of carbon dioxide was formed. They asked the volume. But because we know this, we know that at RTP 1 mole is equal to 24, we can use it in our ratio, right? So we don't have 1 mole, we have 0.027. So we can write out 1 mole is equal to 24 cubic decimeters. That's a fact. So if we have 0.072 moles, what's that going to be? Well, it's going to be cross multiplication. So it's 24 times 0.072, right, divided by 1. And it gives me, let me use a different color, 1.728 cubic decimeters. Wow, where's my mind of this? Right. So, guys, we need to perhaps obviously have a bit of a look at that. And Richard and Christian, you guys missed my first trimester, so we definitely need to get back. This is our first topic that we did, is our mole calculations, our stoichiometric calculations. We need to work through it. I'll make an arrangement with you guys, and perhaps those of you who feel uncertain about it, this is something that we'll need to spend some extra time on after our mid break, right?
Sir?
Yes.
This I completely understand.
Oh, fantastic. Well, that's good.
I just got one question. I kept the moles in fractions because it's more accurate.
Mm-hmm. Yeah, because then you work with your full number. That's fine. As long as the fraction is not your final answer, then I'm happy. That's fine.
Oh, okay, good. All right.
Was that your question, Richard?
Yes.
Ah, fantastic. No good. And then all good. Right. Okay, let's move on to my second question in here. Ooh, jumping. Right, so crude oil is a complex mixture of hydrocarbons. Now they say, explain why the hydrocarbon molecules in crude oil have different boiling points. Now listen, this is due to the intermolecular forces. So I would make a statement and say, listen, boiling points or melting points, boiling points in this case, depend on intermolecular forces. All right, and the intermolecular forces in pure hydrocarbon is van der Waals forces. Van der Waals forces depend on the size of the molecule. The greater the molecule, the greater the number of electrons. So large molecules with more electrons, more attachment points, have more van der Waals forces, therefore higher boiling points. Right, so that would be my explanation for the 2 marks that I think are questions. Right. B, some of the hydrocarbons obtained from crude oil, and now it's a bit covered, it's processed further by cracking. Right. So suggest why some hydrocarbons must be processed further. Well, remember, you have large, long hydrocarbon chains, and we want to break it into smaller, more useful alkanes. So this is essentially the definition of it. And it's very important that you have the smaller, more useful alkanes in there. Right? That is really important. Happy with that still? Creating of 1 mole of that C12H26. I'm not even going to pronounce that for now. I'm going to have a tongue twister. Produces 2 moles of ethene, 1 mole of another hydrocarbon. Okay, so I can write that down. I don't have a problem because they tell me it is C12H26. It breaks up into 2 ethene molecules plus something else. That's something else. We must just make sure that my carbons and my hydrogens add up. So subtracting 4, I get 8 carbons. Subtracting 8, I get 18 H's. Right? That's my equation. Ethene can be used in the production of polyethylene. Give a full name for the process used in production of polyethylene. Well, it's addition polymerization. And guys, we don't do any other polymerization reaction. Only when we get to A levels again, we look at condensation type of polymerization. So we only do addition. So don't come up with any weird answers. Addition polymerization. Give 2 reasons why polyethylene should be reused or recycled rather than thrown away. Well, conserve non-renewable resource, non-biodegradable. You guys have got this in biology, geography, you know, just regurgitate again on that. Happy with that? Okay. Let's look at my IV. And they say a part of a polymer chain produced by the same type of process as polyethylene is shown. All right, so here's an addition or a polymer, and it shows me that's a CH2C, CH3C, OOCH3 in there. And from this, now they want me to do what? They want me to give the displayed formula of a monomer. So what's the monomer? I can see this is my repeat unit. That's my repeat unit in there. So I need to draw the monomer, the alkene from which it originates. So let's start with that. I'm going to have my C double bond C in there. This is my C. That's my C double bond. Remember, that's the bond that breaks and produces those 2 bonds to the side. I want a full displayed formula. So I need to give show all the bonds in there. So there's my 2 hydrogens. There's my 2 hydrogens in there. There is a C and H3 in there. Then I have my, how does that look like? It has
So
C, yeah.
what I did is I took that CH3 and moved it to the end. Otherwise, it doesn't work.
What do you mean? This one?
Are we supposed to make 1 of this entire thing or 2 molecules?
No, just one. Just one. Just one. So this is how my molecule looks like. There we go. So it's got that COO in there. That's an ester bond that's in there with the CH3. And there's my CH3 at the bottom. There's my double bond. And it's that double bond that breaks, right? So this is the monomer that they wanted in there. There's no other way to draw this. None whatsoever. Okay, you must make sure that each carbon has 4 bonds in, the oxygen in there 2 bonds. Right, any questions? Right, let's move on. Question number 3. State the name of type of reaction that hydrocarbon undergoes. And being used as fuels while it's combustion. And now they ask, write an equation for the reaction of CH18 as a fuel. Right, so what are we going to do? And I think, Liam, this is your favorite type of question, isn't it? Where you need to balance, isn't it?
No. So balancing.
Yeah, that's what I recall you said. Right, okay, guys, where do we start? What do we do? We always start with non-hydrogen and oxygen. So we're not going to first consider oxygens and hydrogens. What else is in there? It's carbon. Okay, so if we have 8 carbons in my alkane, well, I have 1 on this side. So I'm using a pencil, just quickly. I'm putting an 8 in there. Right. My oxygen occurs in both products. So the only other thing I'm going to look at is my hydrogen. So here I have 18. There I have something multiplied by 2. So what multiplied by 2 will give me 18? Well, 9.
9.
Yeah, so now we have 18 hydrogens, we have 8 carbons, and oxygen, thank goodness, is standing alone. How many oxygens do we have on this side? We have 16 from my carbon dioxide, 8 times 2, plus 9. What does that give me? That gives me 25. How do I get to 25? How do I multiply 2 with to get to 25? And the answer is 12 and a half. So that's
Sir,
yes.
are we allowed to do that in this test?
Well,
Like
test
you.
an exam, you can do it because we can have a half a mole, can't we? A mole
Yeah.
is the amount of a substance, so we can have a half a mole. We can't have half a molecule, though. Sorry,
Yeah.
half an atom. But we can do this. So this is a legitimate way of balancing. So 1, 12 and a half, 8, 9. If you
Yeah.
are worried about it, then you can say, well, now, let's say this is 2, 25, 16, 18.
Yeah.
Okay.
Yeah, that's basically what I.
If you use the formula that I gave you, that's the balancing numbers that you'll get to. If you used this way of inspection that I just did now, then you will get to the 12 and a half, 8, and 9, and that is a 1. Right. Happy with that?
Okay.
Okay.
Yeah.
So it's a relatively easy way of doing it then. Okay, let's move on to my next bit. There's a supply of materials suitable for the uses fuels derived from crude oil, high demand, name the process. Oh, we're busy with cracking again. Okay, so the process is cracking. Then they say, as well as producing fuels, this process produces compounds suitable for use in the production of polymers. One such molecule is butene. So there's butene. What does a repeat, you draw the repeat unit of a polymer that is produced in butene. Okay, so I just left this out so that you
Doesn't
guys.
that mean you have to draw the monomer?
Sorry, say again.
Doesn't that mean? Sorry, sir. Doesn't that mean you have to draw the monomer?
Yes, you do. And this is my blog. You need to do this now.
Okay, cool.
So I'm breaking my double bond in there. So I have my C bond C. And I have my hydrogen going down. There's my hydrogen. There's my hydrogen going down. So my new bond that's formed is there. This is my new bonds form around that. And then there's this methyl group and methyl group towards it. So CH3 and my CH3. There we go. So
So would it be incorrect if we drew the hydrogens on top?
no, not at all. This is a methyl groups on the top. You can draw the hydrogens at the top. You can draw them across. Knock yourself out. It really doesn't matter. It's the same.
Okay.
Remember, there's free rotation around single bonds, so it can rotate whichever way, and it will be in any direction. Okay. Happy? Name the
Yes, sir.
type of polymerization. It's called addition. Addition polymerization.
What other polymerization is there except for addition?
We get condensation, but that's only at A level. We don't do.
That's if you have to remove water.
Yeah, that's when water is expelled in there. So
It's only those. So it's only those two we've got to know.
Yeah. Do you know? No, you don't even need to know about condensation. You do condensation polymerization in biology AS when you work with those macromolecules in there. But for us, we only do addition at this point in time. Right?
Oh,
Yeah. So if they ask what type of polymerization, you laugh at them and say addition, and you go on. Okay. Number 4. To which, oh, I am so sorry. This was again a typing error. It's C14H30, not H3O. Oh my goodness. And it
I
belongs
thought
to.
it was a ketone.
Listen, that molecule didn't make sense when I looked at it and worked through this worksheet. So I apologize. That was a typing error. There's no way that molecule can exist. There's so many bonds in there. It's ridiculous. Okay, so it belongs to my alkanes, right? And now the rest of the reaction makes sense because now they want us again to balance. And look, here's my balancing again. Let's try my method again. So we have 14 carbons. 14 carbons. We have 30 hydrogens. So what do we multiply by 2? 15 by 2 gives me 30. Right? So how many oxygens do we have on this side? Well, wow, 28, because it's 14 times 2, plus 15 gives me 43 divided by 2 and gives me 21 and a half. Right, reaction balanced. Let's move on. Happy with that? Right. Let's go on to another stoichiometric calculation. So this one I've completed, so I'm going to talk you through. You guys are okay. So they give you the C14H30. I've used my balanced equation in there. The first question they tell you is, well, this jet burns 10.8 kilograms of kerosene for each kilometer, and it's flying approximately 8,195 kilometers. So we can calculate it in kilogram. Hint or not hint, they said, please give it in tons. So divide by 1,000, 88.5 tons. I'm going to use reacting masses to solve my question in here. What is reacting masses? Reacting masses is if I have the molar mass of my C14H30, which I calculated as 198, and I have the molar mass of my carbon dioxide, which is 44 times 14 is 616 grams. Right? So what does this mean? It means that 198 grams of this produces 616 grams of carbon dioxide. But we don't have 198, we have 88.5 tons. Or, wow, 88.5 tons. And now we do cross multiplication. 88.5 times 616 divided by 198. And I get to, and remember, because this is a ratio, this is in grams and this is in grams, this is in tons, this must be in tons. So I have my answer already, 275.5 0.3 tons. So this is one way of doing it. You could have gone the alternative route, the route that we've done in the previous one, convert mass to mole, work in mole ratio, from mole ratio, work back to mass. You would have gotten the same answer. It's the same process as well. Right? So this is just a different way of doing it. Happy with that, all of you?
Yes, sir.
Okay, great stuff. Number 5. Oh, here we go again. What is meant by cracking, and outline the cracking of hydrocarbons? So what is cracking? Cracking is the breaking up of large hydrocarbons into smaller, more useful molecules. Okay, and then we get two different types of cracking. We get thermal cracking that uses high temperatures, or we get catalytic cracking that uses a catalyst. And that scores you the marks in there. All right, let's move on to my second last page. I see our timers are running as well. Okie dokes. Oh, this is a good one. Construct a balanced equation. When we have that C14H30 that is cracked and it produces a C7H16. Well, again, if you do the math, the carbons and hydrogens must add up. So the molecule that they were looking for was an alkene, C7H14. Right, so there we go, C7H14. A question that I've asked various times in exams. Oh, you've got two molecules. You've got an ethanol and you've got an ethanethiol. That's slightly different. This one has got an OH, this one has got an SH. And they ask, why is the boiling point of ethanol much higher than the thiol? Give me an answer, please.
The bonds between the OH.
What type of bonds are those? So
I don't know, sir.
Oh, God. We're talking about
Hydrogen bond.
Yeah, intermolecular forces. Right? So whenever boiling point, melting point comes into play, we're talking about intermolecular forces. When there's an OH, we've got hydrogen bonds. When there's not that, this is just carbons, hydrogens, we sit with van der Waals forces. Now, if you talked about dipole, and I know, Christian, you asked about what's polar, non-polar molecules. I'm still getting to that. I'll answer you. I promise I'll produce a little lesson on that, because it does deem something like a 10-minute just background and information, right? I will get to it. Okay, let's move on to our question number 6, guys. We've got 4 minutes. I don't want to restart the one for this recording. Oh, fraction distillation. What has to be done with the crude oil into the column? Right, so this is the theory that you needed to go through. So you need to turn that crude oil into what? A gas by burning, by vaporizing it, whichever way you want to look at it. Okay, what trend in structure is there from fraction A to F? Well, as we go from A, which is refined gas, to diesel oil to residue, there is an increase in molecular size, or you could have said there's an increase in carbon atoms. State trends and 2 other properties. I've listed a few. So you can say the volatility decreases. Right? One's a gas, the one is almost a sticky solid at the bottom. So in that, there's also an increase in viscosity. There's an increase in density, and there's a decrease in flammability. So refined gas will ignite much faster than diesel oil, for instance. So any two of those would have done. Right? Let's get to our last bit in this question. They say naphtha fraction from fractional distillation of crude oil is used as starting material for cracking. Where write an equation for the cracking of C12H26 to form the products ethene and other hydrocarbons in a 2.1 mole ratio. Right, okay, so this is what they want. They have that molecule, it breaks into ethene and another molecule at a 2-to-1 ratio. So they give us the answer in there. What you need to go and do is again look at the number of carbons to calculate. Last question, and then we can do a bit of a discussion or talk about this still. They say use the use of ethene and the use of the other product. Well, ethene can be used in making polyethylene, so polymerization reactions, right, in plastics. Why can it be used in that? Well, it's unsaturated. It's got a double bond. The other one has got 8 carbons in. Octane. Hopefully you've heard about that before. It's fuel or petrol, and it's got the ability to release energy when it burns. That's more or less what they wanted. This would be a very nice question if you got it, because I think it is an easy 4 marks. All right, guys, any questions on this?
No, sir.
So should we memorize all the uses for
No.
each one of the?
Oh, geez, Daniel, thumbs up. There's much more to memorize. Listen, this video is going to cut out now. Let's quickly zoom back in, and then there's a few things that we can discuss, right?